Unusual and Innovative Engineering Solutions Introduction in the Shadow of Conventional Wisdom lies a realm where engineering defies expectation, where solutions emerge not from textbooks, but from the edges of imagination. I'm your guide into this labyrinth of ingenuity, where the impossible becomes not just possible, but elegantly realized. Welcome to our exploration of unusual and innovative engineering solutions, where constraints breed creativity and necessity births the extraordinary. The world you're about to enter is one where buildings breathe like termites' mounds, where discarded plastic bottles become the foundations of homes, and where concrete heals itself like living skin. These aren't fantasies or distant futures. They exist now, hidden in plain sight, waiting to transform how we perceive what's possible. Nature's blueprint, the natural world, has been engineering solutions for 3.8 billion years, perfecting designs we've only begun to comprehend. This ancient wisdom forms the foundation of biomimicry, perhaps the most profound source of unusual engineering solutions. Consider the Eastgate Centre in Harare, Zimbabwe. While conventional buildings in this climate would require massive air conditioning systems, this structure stands as a monument to alternative thinking. Its designer, Mick Pearce, looked not to modern HVAC textbooks, but to the self-cooling mounds of local termites. These termite architects create internal environments that remain at a constant 87 degrees Fahrenheit, despite external temperatures fluctuating between 35 and 104 degrees. How? Through a complex system of tunnels that manipulate air currents, drawing cool air from underground chambers while expelling hot air through vents at the mound's peak. The Eastgate Centre mirrors this design, using similar principles of passive cooling. The result? A building that consumes 90% less energy for temperature regulation than conventional structures of similar size. This isn't just engineering, it's collaborative design with the natural world. Nature's influence extends beyond building design into transportation. When Japanese engineers faced a perplexing problem with their Shinkansen bullet trains, sonic booms created upon exiting tunnels, they found their answer in the unlikely form of a kingfisher's beak. This bird dives from air into water with barely a ripple, a perfect analog for a train transitioning between air pressures. By reshaping the train's nose to mimic the kingfisher's beak, engineers reduced noise, improved aerodynamics, and increased energy efficiency by 15%. Even Velcro, that ubiquitous fastener, emerged from Georges de Mestral's curious examination of burdock burrs clinging to his dog's fur after a hunting trip. The tiny hooks that caught in the dog's fur became the inspiration for a revolutionary fastening system. Waste reimagined, perhaps nothing speaks more to human ingenuity than our capacity to transform what we've discarded into what we need. In regions facing extreme resource constraints, this mindset has produced engineering solutions that border on the miraculous. In Nigeria, plastic bottles, filled with sand and stacked like bricks, have become the building blocks of homes that are not just economical but bulletproof and fireproof. These bottle houses cost 1/3 the price of conventional buildings, while diverting waste from landfills and oceans. This philosophy extends to the Earthship biotecture movement, where discarded tires are packed with earth to create thermal mass walls that regulate temperature without external energy. A single Earthship can divert up to 1,000 tires from landfills, transforming waste into structural and thermal assets. Meanwhile, Dutch engineers have pioneered roads made from recycled ocean plastic. Infrastructure that's not only reducing environmental impact, but proving more durable than traditional asphalt. And researchers at University College London have developed construction materials made from ground coffee waste, creating blocks that are lighter and provide better insulation than traditional options. Engineering at the extremes, some of the most unusual engineering emerges when humans confront extreme environments, places where conventional approaches simply fail. In Bangladesh, architect Mohammad Rizwan didn't try to fight annual flooding. Instead, he embraced it by creating floating schools, health clinics, and libraries. These structures rise with the waters, allowing communities to maintain critical services despite environmental challenges. In arid regions, where water is more precious than gold, fog harvesting nets stand as monuments to elegant simplicity. These mesh structures, inspired by the tactics of desert beetles, capture moisture from passing fog, transforming it into usable water without energy input. A single fog harvester in Chile can collect up to 75 gallons of water daily from seemingly dry air. Beneath the ocean's surface, engineers have created pressurized habitats like SCALAB, allowing humans to live and work in environments we weren't designed to inhabit. And in polar regions, structures built entirely from ice and snow, like Sweden's ICEHOTEL, leverage the insulating properties of these materials to create comfortable spaces in the most forbidding climates. The microscopic frontier, as we peer into the realm of the infinitesimal, engineering takes on an almost magical quality, manipulating matter at scales beyond human perception. Microfluidic labs on a chip now pack entire diagnostic laboratories onto devices smaller than credit cards. These silicon marvels manipulate fluid volumes measured in nanoliters through channels thinner than human hair, democratizing medical diagnostics in regions without traditional infrastructure. The ancient art of origami has inspired deployable structures that can unfold from compact forms into complex, functional configurations. From solar arrays that unfurl in space to emergency shelters that expand from backpack-sized packages, these designs maximize functionality while minimizing transport volume. Perhaps most bewildering are self-healing materials like concrete embedded with bacteria spores. When cracks form, these dormant microorganisms awaken, feeding on embedded nutrients to produce limestone that seals the fissures, concrete that repairs itself like living tissue. We stand now at the threshold of 4D printing, where objects change shape or function in response to environmental triggers like heat, moisture, or light. Imagine medical implants that transform to match a patient's anatomy after insertion, or infrastructure that adapts to environmental stresses without human intervention. Conclusion: these unusual engineering solutions reveal a profound truth. Our most significant constraints often catalyze our greatest innovations. When conventional approaches fail, when resources dwindle, environments turn hostile, or challenges seem insurmountable, human ingenuity finds its most fertile ground. The future of engineering may not lie in grandiose megaprojects, but in these unusual, elegant solutions that work with nature rather than against it, that transform waste into resources, that adapt to extremes rather than fighting them, and that manipulate matter at increasingly fundamental levels. As we conclude our journey through this labyrinth of ingenuity, I leave you with a question. What problem before you might benefit from unconventional thinking? What solution lies not in doing more of the same, but in approaching from an entirely different angle? The most perplexing challenges of our time, climate change, resource scarcity, sustainable development, may find their answers not in the center of established practice, but at the edges where the unusual thrives. Until next time, keep exploring the boundaries of what's possible. After all, today's unusual is tomorrow's ordinary.